Welcome to qnawire.
So we have to find first the final velocity after it travels through that 200-meter incline. So we're going to say that the motion along the incline would be the x direction, at least for that part of the problem. And we can say that essentially Vx final squared equals Vx initial squared plus 2 times the acceleration times delta x. So essentially, we know that the initial velocity is 0, and we can say that the final velocity would be equal to the radical 2 times the acceleration of 1.90 meters per second squared multiplied by the length of the incline, 200 meters. And this is giving us 27.57 meters per second. This would be the initial velocity, 27.57 meters per second, at an angle theta equaling 35 degrees above the horizontal. And so now we can say that it is going to be at a vertical height. We could say that the initial vertical height this would be essentially 200 meters multiplied by sine of 35 degrees. And this is giving us 114.7 meters. So that would be the initial vertical height before it even leaves the incline. And so now we can say that this would be equal to y initial. And we can say that here the velocity x initial would be equal to 27.57 meters per second multiplied by cosine of 35 degrees. And this is equaling at 22.57 meters per second. Velocity y initial would be equal to 27.57 meters per second sine of 35 degrees. And this is equaling 15.81 meters per second. So we know that here we're going to let the acceleration in the y direction be negative. So this would be negative 9.80 meters per second squared. And in free fall, we can say that the acceleration in the x direction would be 0 meters per second. So there isn't any acceleration in the x direction. We're going to say that the initial x position would be equal to, similar here, 200 meters times cosine of 35 degrees. This is equaling 163.8 meters. So after we have all of our knowns and solving for the variables essentially after it leaves the incline, we can then see that we can then find the maximum height essentially. So then we have that at the maximum height for part A, at y max, we could say that the velocity in the y direction final would equal 0 meters per second. So we can then say that Vy final squared equals Vy initial squared plus 2 times the acceleration in the y direction times delta y. We know that then we're going to cancel this out, and we have that delta y is equal to negative 15.81 meters per second quantity squared divided by 2 times negative 9.8 meters per second squared. And this is equaling 12.77 meters. So we can say that the maximum height, y max, would be above ground, would be equal to delta y plus our y initial previously. So this would be 12.77 meters plus 114.7 meters. This is giving us approximately 128 meters. This would be our answer for part A. For part B, we can find the time in the air. So we can say that for part B, we want to find the greatest horizontal range. So again, first time in the air, because finding the time in the air would give us essentially how far it is traveling at a x velocity. So we can say that first we can calculate the time in the air from the vertical component of the projectile motion, and so we can say that delta y. In this case, we're gonna say negative 114.7 meters, and then we can use delta y equaling Vy initial t plus 1/2 a sub y t squared. And so this is going to be equal to 4.90 meters per second squared times t squared minus 15.81 meters per second times t, and then minus 114.7 meters. This is equaling 0, and as you can see, this is a quadratic equation. So you can use your solve function in your TI-84, 85, or 89 in order to solve for this, and we find that t is giving us the only positive root, 6.713 seconds. So now we can solve for the range, and we can then say that the change delta x would be equal to Vx multiplied by t, because again, there isn't any acceleration, so we don't have to account for the acceleration term. So this would simply be 22.57 meters per second multiplied by 6.713 seconds, and delta x is essentially equaling 151.6 meters, and we find that the maximum horizontal range of the rocket x would be equaling 163.8 meters, our initial x position, before it even leaves the incline, or essentially the moment it leaves the incline, plus 151.6 meters, our final horizontal range of the rocket, 315 meters approximately. This would be our final answer for part B. That is the end of the solution. Thank you for watching.